Magnets are super cool. They have two ends, a north pole and a south pole. If you take two magnets and try to push their north poles together, you will feel a force. It's a pushing force. The magnets don't want to touch. This is called repulsion. It's like they are saying, hey, get away from me. The same thing happens if you try to push two south poles together. They also repel each other. But if you bring a north pole close to a south pole, they pull together. They attract each other. This invisible force is what makes magnets so fascinating and useful in our world. Now let's imagine we use this pushing force to make something float. This is called magnetic levitation, or maglev for short. Think about a toy train that floats above its track. The track is lined with magnets, and the bottom of the train is also lined with magnets. If we set it up just right, with the same poles facing each other, the track will push the train up. The train will hover in the air, held up by nothing but an invisible magnetic field. It's science in action, and it's a powerful demonstration of how we can use these fundamental forces of nature. Let's take this idea and put it inside a pipe. Imagine a long hollow tube. Now let's say we coat the entire inside surface of this pipe with the north pole of a magnet. The whole inner wall is just one big north pole. Then we take a small pod, maybe the size of a toy car, and we coat its entire outer surface with the north pole too. What do you think will happen when we place this pod inside the pipe? The North Pole pipe will push away the North Pole pod from all sides. The pod won't be able to touch the walls. This setup creates a unique environment. The pod is now trapped within a magnetic cushion. The walls of the pipe are constantly pushing the pod toward the center. If the pod gets too close to the left side pushes it back to the right. If it drifts up, the top of the pipe pushes it back down. It's like the pod is sitting in a perfectly shaped magnetic hammock, held in place by forces you can't even see. This is the starting point for our amazing floating pod experiment. Consider the possibilities. It's an incredible concept, all based on a simple rule, like poles repel. So, we have our pod inside the magnetic pipe. The magnetic forces are pushing it away from the walls, top and bottom. But there's another force we always have to think about here on Earth. That force is gravity. Gravity is constantly pulling everything down toward the center of our planet. It's pulling our pod down too. So for our pod to truly float, the magnetic force pushing up from the bottom of the pipe must be strong enough to fight against gravity. It's a cosmic tug-of-war between two fundamental forces of the universe. For the pod to levitate perfectly in the middle of the pipe, these forces must be balanced. The upward push from the magnetic field on the bottom of the pipe needs to be exactly equal to the downward pull of gravity. If the magnetic force is too weak, the pod will sink and rest on the bottom of the pipe. If the magnetic force is too strong, it might push the pod all the way up to the top. But if the forces are perfectly balanced, the pod will just hang there, suspended in mid-air, not touching anything at all. It's a beautiful example of equilibrium in physics. Let's think about this balance. The pod has mass, which is the amount of stuff it's made of. Gravity pulls on this mass. To counteract this, the magnets we use must be powerful. The strength of the magnets in both the pipe and on the pod determines how strong the repulsive force is. For a heavier pod, we would need much stronger magnets to create a big enough push to overcome gravity's pull. Engineers who design things like maglev trains have to do these calculations very carefully to make sure the train floats correctly. Once the pod is floating, it's in a very special state. It's free from the friction that usually happens when an object touches a surface. When you slide a book across a table, friction between the book and the table slows it down. But our pod isn't touching anything. It's surrounded by a magnetic field on all sides, and it's held up against gravity. This creates an almost frictionless environment, which is key to understanding how it will move when we give it a little push. This is where things get really interesting. Now that our pod is floating in a perfect balance, what happens if we give it a gentle push forward? This is where another cool science idea comes in: inertia. Inertia is a property of all matter. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. This was famously described by Sir Isaac Newton. Since our pod is floating and not touching anything, there is almost no friction to slow it down. It's just the pod and the invisible forces around it. In an absolutely perfect, ideal system, which doesn't exist in reality, but is fun to think about, that single push would be all it needs. The pod would start to move forward, and because of inertia, it would just keep going. It would glide smoothly down the length of the pipe at a constant speed, never slowing down. It wouldn't need an engine or any more pushes. It would just travel on and on forever, as long as the pipe continued. This is the dream of frictionless travel, a vehicle that moves forever after one initial nudge. Think about being in outer space. If you are an astronaut and you throw a wrench, that wrench will travel in a straight line forever, unless it gets pulled in by the gravity of a planet or hits something. Our pod inside the perfect magnetic pipe is a bit like that wrench in space. The magnetic field keeps it centered and away from the walls, so it doesn't bump into anything. The initial push gives it its starting motion, and inertia makes sure it continues that motion. It's a beautiful, simple example of the laws of physics at work. This principle is the core idea behind concepts like the Hyperloop. The goal is to create a tube with very low air pressure and use magnetic levitation to float a pod. By removing both air resistance and friction from the track, the pod can travel at incredibly high speeds using very little energy. In our perfect imaginary pipe, the pod would be a perfect example of this. It would be a perpetual motion machine of sorts, but one that obeys the laws of physics because nothing is creating new energy. It's just preserving its initial motion. But as we know, the real world is never quite so perfect. So, in our perfect thought experiment, the pod glides forever. But what happens in the real world? Even if we built this pipe perfectly and pumped all the air out to create a vacuum, the pod would still eventually slow down and stop. Why? The reason is a sneaky, invisible force created by the magnets themselves. This force comes from something called eddy currents. They are tiny, swirling currents of electricity that are generated when a magnet moves near a conductor, like the metal in our pipe. It's a fascinating bit of electrical science. As our magnetic pod moves through the pipe, its magnetic field is also moving. This moving magnetic field interacts with the conductive material of the pipe walls. According to the laws of electromagnetism, a changing magnetic field will create an electric current in a nearby conductor. These are the eddy currents. They swirl around in the pipe's walls like little whirlpools of electricity. They aren't something you can see, but they are definitely there, and they have a very important effect on our moving pod. These currents are a natural consequence of motion and magnetism. Now, here's the crucial part. These eddy currents don't just appear and do nothing. They create their own magnetic fields, and these new magnetic fields push back against the magnetic field of the pod that created them in the first place. It's like the pipe is fighting back. This pushback creates a resistance force, a type of drag. It's often called magnetic drag or magnetic braking. This force always opposes the motion of the pod. It's like trying to run through water. The water pushes against you and slows you down. So, even in a vacuum with no air resistance, this magnetic drag is always present. The faster the pod tries to move, the stronger the eddy currents become, and the stronger the magnetic drag gets. This is why our pod, even after a good push, will not move forever. It will glide for a long time, much longer than a book sliding on a table. But the invisible force of magnetic drag will constantly be there, gently slowing it down until it eventually comes to a complete stop. In the real world, perpetual motion is not possible, and eddy currents are one of the many reasons why. Science is cool,